Hello. So this is a video about COMP345. This is week 7, slide set 7. This is video 2 of 3 for this slide set. In this video, we're going to talk about value and reference semantics. This has to do with polymorphism, as when you use polymorphism, you should have reference semantics, but there's still a possibility to have what is called reference semantics in C++, which is quite unusual for as far as object-oriented programming languages go. So let's go to the slides. So this is about value semantics and reference semantics. So what is value and reference semantics? So very simply stated, this is kind of a simplistic description here. Value semantics is when you manipulate objects, when you are creating objects, or you pass objects as parameters, or you access objects, or you copy objects. You actually are copying the objects themselves. Whereas if you use reference semantics, you actually are passing references or pointers, you manipulate pointers, you access pointers, or you copy pointers, okay, or references. So that's the difference between the two. And that's a very simplistic description. So what's particular about C++ is that it allows you to use either of these two models, okay, of computing objects, which is very unusual as far as object-oriented programming languages go. For example, like in Java, you have only reference semantics. So even though it appears in Java that you're never using pointers, what you are actually using all the time is pointers or references. So Java has only reference semantics. It cannot use value semantics except for the basic types. So why this choice of actually having C++ being able to use either reference semantics or value semantics? Why not go with only reference semantics? As we shall see, as I explain for a little bit further, reference semantics is something that you actually need in many cases. Okay, so why would you want to have also value semantics? It seems to be that it's making things more complex. Yes, it is making things more complex, but there's also advantages of using value semantics. So as a general concept, the idea of reference semantics is that let's say you would create an object, and then you would have a reference that refers to this object in memory. The idea being that you can have several references potentially that are all pointing, reference or pointers that are all pointing to the same object. Now, this has to do, or is somehow related or is similar to the notion of a global variable. Global variable is a variable that is declared in a global scope, which can be accessed or changed even by any scope that is part of the global scope. Okay. So the thing is that you can then have different scopes in your program that can alter a common variable. So that then there's something that binds each of these scopes together. Potentially the execution of each of the scopes may depend on the value of this global variable, which may be changed in any of the scopes. Same thing happens when you have a single value that is pointed to or referred to by different pointers or references. So these references actually refer to the same object, and no matter where they are in your program in different scopes, if one of the references is changing the value of the object that is being referred, then any of the other references when you access it, would actually access the changed value. Okay, so that's what is one of the both power as danger of actually using references. So that's something that you want, that you very often need to be able to have, to basically share the same object by having different references. I'll give an example later. So by using reference semantics, same shared value can be changed in different scope. That which I just explained may actually severely complexify your design, okay? Because then suddenly different parts of your program share the same value. So each of them can actually then change the possible behavior of the other part through a change on this common value that they use or that they share. Okay. So yes, this is desirable very often, but if this is happening all the time and you have no way around it, that can actually lead to more complexification of your, more complexity of your design, make your design more confusing and potentially error prone. So also reference semantics requires more complex memory management. So if you have one object that is being referred to by many different parts of your program, then, for example, one of the complex things is which of these parts is then responsible from deleting this object. Okay, so that's one of the main problems when you deal with reference semantics. That's basically why in Java you have the garbage collector. The garbage collector, what it does is that it maintains a counter for each object that you have created that is being referred to at different places in your program. It maintains a counter of how many references are actually pointing to this object. And then as soon as this counter gets to 0, then this object is potentially subject to garbage collection later on. Okay. So basically there's a counter, and then when it's not referred to anymore by anything in the execution of the program, then it can be freed. Okay. Now you can say that's a very simple thing, simple mechanism, but it requires management, and it requires also that the garbage collecting does a sweep from time to time to actually delete what is to be deleted. So yeah, reference semantics, if that's the basic model and that the references are to be allocated and deleted automatically, then that requires quite elaborated mechanism, which C++ decided to do away and basically let the programmer have to manage their own memory resources, which is one of the main problems as we saw in C++. So fact of the matter is that sometimes reference semantics is not something that you need. And if that's not something that you need, then that's basically the cost involved in managing your references, especially the deallocation, potentially the automatic deallocation brings a cost. But if you don't need references, then if you can't do away with the automatic management, then you basically have to use something which implies a cost, and you don't need to actually use this thing. Okay, that's one of the concepts also with C++ and C, is that if a certain mechanism is not necessary for the execution of your program, it should not induce a cost. Okay, that's why C++ and C had decided to enable value semantics, because sometimes reference semantics is not needed and induces a cost. So then you might say, then if reference semantics induces a cost, then why not always use value semantics? Now, as I hinted at before, very often you actually need to have reference semantics. So that's something that you must have in a programming language if you want to design programs. There are desirable features of programs that require that you have references. Okay. Very often you would define, for example, two different objects that share the same resource. Okay. So for example, in a project, we have a map. A map is the graph, sorry. The graph is essentially a set of territories, and each of the territories, there's a list of neighbors, which are also territories, okay? So the fact, well, let's say we have a graph like this one here. Let's say this is your territory A, B, and C. So A has as a neighbor B, and A has its neighbor C, C has its neighbor B, and B has a neighbor A. Now, if you would only have value semantics to express something like this, that would mean here that this object A, the territory A, would need to contain an object of another territory, which is an object, the object B, which is another territory. Okay, so territory A would need to contain somehow as a value the territory B, as well as the territory C. And then the territory C will also need to contain the territory B. So you see that if you don't have references here, then you could not have the fact that A and C are sharing the same territory B as the same value. Okay, because these are values. You could duplicate B, but then when you change B, then you would have to inform A and C that their own B has changed, whereas it should be the same B. Okay, so if you want to have things that point to the same place, basically are referring to a common state across different objects, you need to have references. It gets even worse if you have cyclic references like this. So A actually contains a B, and then the B contains an A, which contains a B, which contains an A. So that's basically creating an infinite loop. If you want to create the object A, then it would need to contain a B, which would need to contain an A, which would need to contain a B, and so on and so forth. Okay, so that just doesn't work. Okay, if you have value semantics, you cannot have cycles because that leads to create objects of infinite size. Well, when you want to know the size of a node or a territory, then you basically compute what is the addition of all the sizes of all of its components. So if you have cycle like this, then that basically creates infinite size. Okay. So that's one reason why you cannot have only value semantics, because you could not have cycles and you could not have objects that share the same state, which is very often something you want. Another question, value semantics leads to copies being made, because the notion of value semantics is that when, for example, you pass a value by value to a function, then as we saw earlier, a copy of this value is being made, which is then being processed internally by the function that received it as a value. Okay, so that very often value semantics implies that there are copies of objects being made, okay, rather than passing around references. Okay. So if that's so, wasteful of resources, so why are we relying so much? Why does C++ want to use value semantics if it's likely to consume more memory than reference semantics? There's a lot of, as you may know by now, C++ is a very well optimized. C++ compilers are very, very well optimized. One of the things they do is what's called copy elision. So copy elision means that when you are actually generating the code for a certain statement or expression, there are some times where you can actually avoid making copies as an optimization step. So C++ compilers would very often perform this copy elision. We saw that when we saw that we saw that earlier when we discussed the creation of objects. So when you when you declare an object and you assign it to a newly created object calling a constructor, it may appear that there's the assignment operator that is involved here, which would make a copy, but then there's copy elision that is happening here. And what's actually happening is that the copy constructor is going to be called instead of a constructor being called, and then the assignment operator, which would make a copy. So there's a lot of optimization steps that are implemented by C++ compilers that avoid as much as possible for superfluous copies to be made, even though it's using value semantics. Another reason why reference semantics is not so good is that every time you want to use an object that is a reference that is referring to an object, you have to dereference this pointer or reference in order to access the object. This dereference operation takes a little bit more time, but if you do it every time you access an object, that adds up to, nanoseconds can quickly add up to minutes when you're doing a lot of operations, okay, or at least seconds. So yes, dereferencing, when you do it very often, leads to inefficiency somehow. So that's why sometimes value semantics is more desirable. When you use value semantics, if you have an object, for example, that is composed of different parts, the compiler will actually use offsets, which are calculated at compile time to refer to the members of the object. Okay, so it doesn't need to calculate at compile time or to use dereference in order to access the members of a class. It would use offsets, which are computed at compile time, which are not computed at runtime. Okay, so that's another reason why value semantics is desirable. Also, when you use reference semantics, if you have value semantics, then only the object needs to be stored in the computer's memory. Whereas if you use pointers or references, then you need to have another single cell that actually contains the pointer that points to this value. So every time you have an object, you consume one more memory cell. So if you have hundreds of thousands of objects, then you consume potentially a lot more memory. Yes, so references is a little bit wasteful of memory compared to values. So value semantics also brings another problem, which is called object slicing. So here we are, it's important to understand the difference between value semantics and reference semantics. One of the detrimental aspects of using value semantics is if you're trying to assign objects across inheritance hierarchy or graph. If you're assigning objects of the same type, everything goes fine. But if you're starting to want to assign an object of a subtype to a container or variable of the supertype, things start going wrong. Okay, so that's what is called object slicing. So here's the case of when everything goes fine. Okay, so here I have my main function here. I have my dog class. Dog class is what I have here. So the dog basically contains a breed field, and the dog is actually a subclass. So I forgot to write this here. The dog is a subclass of pet, which contains a name. Okay. So here basically I'm creating two dogs, and then which creates, so this main function executes here, and then that is my vdog1 that is here, and there's my vdog2 that is here. Then what I do is I say vdog2 is equal to vdog1. So essentially what happens here is that the content of that here is copied directly into the content here. Okay. So that can be done very efficiently by basically taking this block here and copying it as a block right there. Extremely efficient kind of copying. Okay. Well, eventually it's more complicated than that, but let's put it this way. It's like when we were talking about arrays, the static arrays. They were very efficient. Why? Because you knew that the entire array was stored in contiguous memory space. So this assumption here makes it possible that you would have very well optimized operations. Okay, so kind of the same thing is assumed here. Okay. So if I copy vdog2, vdog1 into vdog2, then it's actually copying here. Okay, so basically directly copy this here into that here. Then if I call this f function that receives a dog and assigns a name to this dog and then returns this dog, as we saw, it would make a copy of vdog2 and actually passing it into the function f here. So the parameter of this function is here. So it's basically taking this memory space here, copying it here, and then the f function operates on this copy here. And then this is returned here. So the copy of this is returned and then copied into vdog2 back here. Okay. So all of this is using value semantics. So what is being passed around and copied here is the entire object. Okay. So this can be made very efficient. Okay. Of course, then the objects are being copied and so on. So that's a little bit more wasteful of memory. But as we saw earlier, the compiler would actually be able to optimize when copies can be avoided to minimize this overhead. So this works very well here because all the types that we have is the same type. So that works very well, but it doesn't work so well when you add subtypes, interaction between different types across inheritance hierarchy. So if you would be copying, for example, a dog into a pet, as we will see in the next slide, and things would start happening not so smoothly because a pet contains only a name and does not contain a breed. So what happens if you're trying to copy a dog into a pet? So in this case, basically the dog would lose its breed information and only the name would be copied. That's what is called object slicing. So here is the pet class, and then you have the dog class here. The pet has constructors, a copy constructor, and then a string constructor, has a virtual destructor, and a virtual function named print. There's also a function print inside of the dog. And this is where the polymorphism will eventually be happening. Because in this first example here, we're using value semantics, we will see that the polymorphism is actually not happening because we're not using pointers. Okay. That's what links this whole discussion here with polymorphism. If you want to have polymorphism, you need absolutely to use reference semantics. If you don't use references or pointers, there's no polymorphism, as the example would show. And then each of the pet and the dog also has their own assignment operator. Whereas the dog assignment operator is copying the breed after it had actually called the pet assignment operator, which would copy the name. Okay. So here we go with the start of the example here. So here essentially I'm creating my dog and then a pet. So this dog is named vdog1. So that's this object here that's residing on the stack. Its name is Tiny, and then his breed is Great Dane. Then I'm creating a pet named vpet1 using the default constructor. In the start, of course, it does not have its name here because I did not provide any parameter to the constructor. So this initially is empty. Then I actually create a vpet2, which is a pet. And then I pass this vdog here, which is Tiny Great Dane, which is this object here. But what I'm creating here is a pet, so it has only name. So eventually we see that the copy constructor of vpet2 is the pet copy constructor. And what it does is only initializes name, because of course a pet, the only thing it has is a name. It does not have a breed. So that's why when it calls this copy constructor here, copies only the name here. Okay. So even though you might think, well, I used a dog to initialize my pet, maybe you thought it's going to be a dog. No, it's going to be a pet, and it's not going to have a breed. And this information about the dog was a Great Dane. The dog that you used to create this new pet here, it was called, it had a breed, Great Dane, but as you created this pet using the copy constructor here, it lost the information about the fact that it was a Great Dane. And the only thing you know now is that it has a name and it's Tiny. So, and then, which is more to the point here, is I'm trying to apply to copy the vdog1 into vpet1. So I'm trying to copy vdog1 into vpet1. So you see that vpet1, the only thing that has is name. So when I'm actually copying vdog1 into vpet1, it loses the breed and only the name is being copied because that's the only thing it can contain. Okay, so that's two cases here of the object slicing. Here you try to copy a dog into a pet. The pet can only take name, so that's the only thing is copied, and the rest is lost in the copy. Same thing when you call the copy constructor here. So that's what do two different cases of object slicing. So you see, as soon as you start use value semantics across an inheritance hierarchy, things are not working so well. And you have to be aware that this is how it behaves. So basically here you lose information. If you're trying to copy an object of a subkind into a container of a superkind, then it's going to lose the information that is not in the superkind, the superclass or the base class. So value semantics is applied when the manipulated values are not pointers or references. So anytime you're not using pointers or references, it is using value semantics. Okay. So the same applies when you pass a parameter to a function. If you don't define this parameter as a reference, then it is going to be passed by value, and a copy is going to be made. And when the object is being received, if it is received as the base class, the same thing is going to happen, as I will show in the next example. The reality is that most object-oriented programming languages don't ever use value semantics. There's no such thing as value semantics in Java except for the basic types. Okay, so that's why it might be coming to you as a very alien and what the hell is this kind of idea? to you as you are a Java programmer. That's one of the things you have to know when you deal with C++. That's one of the many reasons why C++ people find it weird. Yes, it is weird, but it's made for being optimized. So that's why it gives you different choices, which are more advantageous in some cases and more efficient in some cases. Okay. As I explained earlier, if you use only reference semantics and you never allow value semantics, it may lead in some cases to have inefficiencies. Okay. That's why C++ enables you to use value semantics. So here's a more complete example. By the way, this example is in the lab examples. So I invite you to go there and look at the examples, make sure you understand them, and then listen to the videos and go to the labs also. Okay, so here I have my vdog1 here and my vpet1 here. So the difference here is that I'm actually eventually calling this function. It's doing some of those things that I already explained before, except that eventually it's calling this function. So I have my vdog1 here, which is tiny and Great Dane, contains tiny and Great Dane, so it's a dog. Then I create my vpet1 here. Of course, here it's empty for now. Then I create my vpet2 here out of the vdog1, but as it is being copied here by the copy constructor of course can only copy the name. So then the breed of the dog is lost in the copying process of creating this object by the copy constructor. Then I assign vdog1 to vpet1. Then I go vdog1 and I try to put it into vpet2. No, vpet1 here, sorry. So vdog1 goes into vpet1. So you see here, the only thing I can copy is the name of the dog, vdog1. Okay, so there's slicing that is happening here too. Then one of the things I wanted you to understand through this example is that if I call print on vdog1, then that's going to eventually call print of what? The type of vdog1 is dog. So this is going to be calling the print of the dog. Okay. Even though print, the important thing here is that the dog, the print is a virtual method. Okay, so for now that's fine. Okay, but here for this one, here I'm calling a print print of vpet1. Vpet1 is of type pet, so that's going to call the print of the pet class. Then eventually I'm calling the print of vpet2, which is a pet. The thing is that I had used a dog to actually create this pet. So I might think, well, it should call dog print and not pet print. But as it's using value semantics here, then the only thing that's going to be of concern for the compiler and runtime system is what's the type of this as being declared. It's actually pet, so it's going to call pet print. Okay. The important thing to see here is that if you don't use references and you don't have a possibility for an object to create an object of a superkind and have it instantiated with an object of the subkind. Okay, you don't have this notion here. Okay, objects are of one kind, and you cannot have this interrelationships between superkind and subkind. Okay, or base class and subclass. So that's why here it's calling the pet print. Okay. Even though you initialize this pet using a dog. So essentially here the dog lost its identity as a dog and became a pet in the copying process. The type of the value is pet. That's why it's calling pet print. Then eventually I'm calling this function here. That's another aspect of value semantics. Here I'm passing this parameter as a value. So it's passed by value. So even though here I'm passing this dog into this function here, it is actually during the copy process, it is copied into a pet because that's a pet that is being declared here. So as far as this function is concerned here, what it is processing, it is a pet. The type of what is being processed is a pet because the copy it has is a value that is of type pet. That's why when it calls print, it's going to call pet print and not dog print. So it's going to have somehow forgotten that in the copy process, it's going to have forgotten that this used to be a dog. Okay, because of the object slicing that happened, and because this is value semantics, which copies the dog into a pet. Okay, so you see that if you use value semantics, even though you may have declared polymorphism in your classes, if you use value semantics, it's not going to make use of your polymorphism. Okay, that's something that's very important to understand when you design your C++ programs. If you want to use polymorphism, then you would have to use reference semantics. So here's how it goes. So essentially here, this is exactly the same example, except that I'm using reference semantics. So how do I do that? For example, all of the objects that I'm going to be manipulating, they are going to be pointers to these objects. Okay. So here I'm creating, I'm declaring a pointer to a dog, and then I'm instantiating a new dog, and I have this pointer point to this new dog. So essentially my pdog1 here is on the stack. It's a pointer that points to a dog object that is contained in the stack, the heap. Then I create another pointer named ppet1, which is residing on the stack of the main function here, the stack frame of the main function. And I'm creating a pet on the heap, and I make this pointer assigned, the pointer that is returned by the new operator is assigned to this value ppet1. So the value is a pointer, so then ppet1 is now pointing to this value of type pet here. Then here I am creating a pointer to a pet named ppet2. And then here what I do is I make it point to an object of type dog. Now this is allowed because a dog is a pet. Okay. So then I have, as a result of executing this line here, then what I have is a ppet2, which is pointing to this new object of type dog. Okay. Which was created using the copy constructor that received this dog here that I already had constructed, or the reference to this pdog variable that points to an object of type dog that is then passed to the copy constructor of dog and then assigned here. It's important here to understand that when you have this assignment here, it's not the assignment of a pet or a dog, because this is an assignment between a pointer to another pointer. Here, new returns a pointer, and this pointer is assigned to the memory cell that contains this pointer. So the type of value that's being manipulated here is not pet or dog, it's a pointer. So it does not use the assignment operator of either pet or dog. Okay, so one thing that's very important to understand. Okay, so let's say here we want to create another object ppet3 that is pointing to a pet in this case. So ppet3 is creating an object of type pet that is actually created using a dog. Okay, so this ppet3 is now going to be a pointer to a pet that is pointing to this pet here. Okay, that was created using the dog here. So that's what was used, was created using pet's copy constructor, which can only copy the fields of a pet. Okay, so still you have some kind of slicing that's happening here. Because here, this was the dog was somehow sliced into a pet in this copy construction here. Okay, and then if you, for the same reason as I was describing here, if you go ppet1 is equal to pdog1, what this actually does is takes pdog1, the value of pdog1 is the value that you have here, which is an address, and then copies it into ppet1. So you copy this address inside of this memory cell here. So the effect of this is that ppet1 used to point here, but now it is pointing at the same place where this was pointing. So this pointer is now pointing here. Okay. So this assignment here is not an assignment between a pet or a dog, it's an assignment of a pointer. Okay, so your assignment operator of your class is not going to be used in this case here. Then if you, and that's where the most interesting part here from the perspective of polymorphism is happening. If you call print of pdog1, pdog1 is pointing to a dog. So that's eventually going to call dog print. Okay. Then if you call print of ppet1, then it's going to eventually ppet1 is now pointing to a dog. So it's going to eventually call the print of dog. Even though ppet1 is of type pet, it is pointing to a dog. So in this case, the reference semantics is going to somehow enable the polymorphism. Even though this object is of type pet, it is pointing to a dog. So if you call print on it, it's going to call print of dog. Okay. So essentially that's, okay, so let's continue. So ppet, if you call ppet2.print or arrow print, ppet2 is pointing to this dog here, so it's going to call dog print. Whereas if you go ppet3 print, ppet3 is pointing to this pet here, so it's going to call pet print. Okay. So what is important to understand here is that when you use reference semantics, the type that is being used to determine which of your virtual functions is going to be called is the type of that is actually pointed to by the pointer. Or basically, it's going to use the most specific type of the two, basically. It's going to use the type of what is being pointed to by the pointer. Another aspect of it is if you pass by reference to a function, like here we're passing by reference. So if I pass a dog to this function here, even though it's received, its parameter is saying that it should be a pet, then because it's passed by reference, then this dog here, pdog1 is actually passed onto the function. So which makes actually this value here, this is what is passed onto this parameter here, which makes this pointer or this reference actually refer to this dog object here. So even though from the inside perspective here, this is declared as a pet, this is a reference to a pet that points to a dog. That's why if you call .print of pet, of a pet, it's going to call the print of a dog and not print of a pet, because it considers what's the type that is being pointed to by the pointer, which is something that you cannot have if you use values, because the values are don't have this notion that they can be of a certain declared of a certain type but contain a value of a subtype. There's no such thing as this when you deal only with value semantics. So that's it for that. So next thing, we'll see how it actually happens at runtime, that you can have reference semantics and polymorphism. One of the things is we'll see that it uses this notion of function pointers. So that's why we'll start by explaining function pointers. And then eventually we're going to describe what is the notion of the V tables for the implementation of the polymorphism. So that's it for this video. Thank you.